I want to look at aliasing and what happens to frequencies when you get aliasing. If we look at this document here, Module 4 document, and we consider a high frequency sine wave and we sample it as we take samples at certain intervals. Say we take samples like here and here and here and here and here and here. If we take those samples and then try to make up a signal, or in our case an image, from those samples, we won't get the original signal, we'll get a lower frequency signal. This is an aliased signal. We'll join the dots up in the best way that we can, which is interpolate between them, but not linear interpolation, not even cubic interpolation. It's called sync interpolation is the best way to interpolate. But if you use the best way, this is the shape you get. A sine wave, but at a lower frequency. And that's what aliasing is all about. If you don't take enough samples, you get a lower frequency wave when you try and reconstruct from those samples. And then the question is, how many samples should you take, or how frequently should you take them? And the answer we mentioned before is you need to take at least 2 samples per period of the wave that you're sampling in order to recover that wave when you do the reconstruction. At least 2. 2's the absolute minimum. Better if you do more than 2. And this is the same as saying that the sampling frequency, that is the number of samples per second that you take, the sampling frequency should be greater than twice the frequency that you're sampling. Or if you're sampling a mixture of frequencies, at least twice the maximum frequency in that mixture. You should choose a sampling frequency at least twice. Better of 3 times, 4 times. So these two are the same thing. This is in the frequency domain, and this is saying it in the spatial domain. And this is the Nyquist sampling theorem. Now, if we look at the book, on page 29, we see that Nyquist sampling theorem there. The sampling frequency must be at least twice the maximum frequency in the signal or the image that you're sampling. And half of the sampling frequency is known as the Nyquist frequency. So if we divide through by 2, the Nyquist frequency must be greater than, better if it's a lot greater than, the maximum frequency. Here we haven't taken enough samples, and so the reconstructed wave is at a lower frequency than the original. Here we've taken just enough samples and we interpolate between them using sync interpolation. We can get the sine wave back just about when we take 2 samples per period. So we can get back all the frequencies up to the Nyquist frequency. Frequencies above the Nyquist are undersampled and they appear as lower frequencies in the reconstructed image. And that's what we know as aliasing. These lower frequencies are the aliasing frequencies. We looked at this example a long time ago, I think, in a system with 20 micrometer pixels. The sampling frequency was 5 per millimeter. The sampling frequency is the inverse of the pixel size and vice versa. So the sampling frequency to get an image with 200 micrometer pixels is 5 samples per millimeter, 5 millimeters to the minus 1. And so the highest frequency that you can get is half of that, is the Nyquist frequency. So here we've got our sampling frequency is 5 per millimeter. Half that is the Nyquist frequency 2.5. We can't see any frequencies in the reconstructed image greater than 2.5 if we sample at 5. If we have a frequency at 3 and we're sampling at 5, the Nyquist is 2.5. The 5 turns up in the reconstructed image as a frequency of 2. It's mirrored about that Nyquist frequency. It occurs as far below the Nyquist frequency as it was above in the original. And again, with a sampling frequency corresponding to 200 micrometer pixels, if we had a frequency of 4, it will appear in this digital image at 1. It'll be mirrored about the Nyquist frequency. A frequency up here of 6 will get mirrored first about multiples of the Nyquist, say the second multiple of the Nyquist, which is the sampling frequency. So it would get mirrored down to 4, but it's still above the Nyquist, and then it would be mirrored again down to 1. And so a 6 would appear as a 1. I want you to look through that worked example again and see if you can't figure that out.